Okay, hi everyone. Welcome to Edison Bob. This is a Polkalytics live stream, and we're going to look at Polkadot, Parachain, Netflows today. This is part 2 of the live stream. Let me get my mic in order here. Okay, it's a little bit crowded here today. So what are we going to do? I was thinking of doing a little bit of whiteboard here today. So the topic is Polkadot, Parachain, Netflows. So what does it mean? Let's give us some space here. Whoa, that's not what I want. Okay, so no matter. Polkadot, Parachain, Netflows. So what we're going to look at is how does value flow between parachains. So in the Polkadot ecosystem, you have the DOT token and you have several parachains that are connected in the ecosystem. And so DOT can flow in and out of those parachains. It can flow between those parachains. And I think it would be very interesting to get a little bit of an insight into how the value is flowing. So this is what we're going to look at today. This is part 2 because in the first part, which was also a live stream, I basically looked at what are all the parachains that exist in Subscan, wrote down all of the addresses, let me show, and basically wrote down all of the addresses for Polkadot parachains, for Kusama parachains. I think we focused only on those that have actual XCM history, so a history of value flow between parachains. And so last time, where did we stop? We stopped at me putting in a few jobs into the Polkalytics engine, so to say. And so basically I scraped a lot of those addresses through my Google Cloud infrastructure. So my Google Cloud infrastructure consists of several parts. One is the BigQuery database, which is a big data warehouse. So it's basically a bunch of SQL tables that are non-relational and they can keep a lot of data. And so we keep all of the blockchain's history there from Polkadot and Kusama. So this is blocks, extrinsics, events, all the calls. And on request, the system can now go through the history of a certain address and see all the balance changes. And so these are historical ones, not only those initiated actively by the account, but also passive balance changes, I would say. So balance changes that were initiated somewhere else on the chain and just influence the balance. So for example, this can be the case when you're staking and you should receive staking rewards. And so you can claim them for yourself, but also anyone else staking with the same validator can claim those staking rewards. So whenever they're flowing into your account, it doesn't always have to be that you're actively engaging with the chain. Sometimes your balance can just update. Another case is when you get sent some tokens. So you need to look at all of those cases and create a list of all of those balance changes. And so what we're going to do today before we go into the technicals is number 1, check the balance changes table. So check out the balance changes table. We're going to see, was the scrape successful? Was there maybe a mistake? This is part of the bread and butter of the data analyst, checking for the quality of the data. And then what is the outcome? So the outcome we want to have is a nice graph of parachains and how much value they held at a certain point in time. This is the outcome. So basically in step 1, we're checking the input. We check the balance change table for the appropriate balance changes. We're going to maybe query it, query, and transform it into a format that we can then use to generate our graph. How can we generate the graph? I think in general, the easiest way to do it would likely be in Python. Python is usually best equipped to quickly come up with a graph or an infographic. Sometimes you can also use TypeScript. I guess there are a lot of good libraries out there. But I would say we're going to use Python and maybe even try to learn how to quickly show some data in a dashboard. Another way how you could do it is, for example, I'm not super experienced with that, but it might actually be interesting. We could even try that. It's a product from Google to show data. It's basically to create dashboards and high-level overview of data. We might do that because this is actually interesting and it could yield some interesting results initially. So query and transform, and then generate graphs. So this is how we're going to do this today. Okay, so step one is we're going to check the balances, the balance changes table. As well, when you have a microphone here. And if you have any questions during the session, please just let me know in chat. It's good to have you here in chat, but these are the sessions where I usually like to take a deep dive into the chain. So this can be 50% boring, then it's 35% me talking some interesting, hopefully stuff, teaching something, and then 15% we will see some results. So we're going to check out Alpha Chain Polkadot. This is how this data set is called. And the table we want to look at is the balance changes. And so this is a very simple table. It has 4 columns. So this is the address. This is a block number where the address changed in balance. What was the new balance and how did the balance change? Okay, so if we preview the data here, you can see this can affect a lot of different addresses. Here you see one address if you go a few steps further down the line, but this is basically a lot of numbers. So we want to first filter it out because there are quite a lot of different addresses that are there. So we want to only see certain data. So that's the first thing you're going to do. So let's do a select, I think star in this case, okay, from Parachain Polkadot, and this is the balance changes table. And then we need a where clause because it's partitioned, and so we ask for the block number, but we are literal, we say everything between 1 and I don't know what, I think this is how many tables we've indexed. So this is nice already, but then we also need to filter for address, and so we say and the address in, and then we need to provide a list. Now it's going to be interesting to see how I can provide a proper list, but let's try it with 2 addresses first, Polkadot addresses first, and if that works out we can make the list a little bit bigger, but I'm thinking maybe it's just like this. So let's see if that works. Okay, this doesn't throw an error, a syntax error, and we're getting results, right? Okay, you see parachains have a lot of balance changes. In this case, it's already 72,000 for those 2. Okay, so this is how we need our list presented. What I usually do in such a case is copy this to a new table here, and then we need a leading and have it like this, and then there's a space, and so this is how we want it formatted. And then we have a few tabs there, but that should be okay. Could even have asked ChatGPT to solve this problem for us. Okay, so this will allow us to scrape through all of those addresses. Okay, and now we do the same here. Ching. And this is now our query to check for all Polkadot parachains. So the query works, I would say, yes. And we say all Polkadot parachains. Okay, there's a little bit of code that will now give us all of those results. And now we have the data. Now we can nicely package it, so we can prepare it and put it into a result table that we want to use. So how about we put it in a, what do we do? Yeah, let's put it into, let's just download it as a comma separated list. And now comes the fun part. Now we have some data and now we can work with the data. So let's check the file. Okay, so the way I would like to transform the data is with a Python notebook. So I'm going to open this on a second screen for a second. So analytics, Netflows. Okay, so we're having a nice Drive folder here, and what we're going to do is to create a new Google Collaboratory. And this collaboratory is basically Python in the browser, and should create a nice sample that we can use. Okay, so this is the Netflows sample. And first things first, we need to upload the file. So runtime, I mean, we will initiate it. So, okay, this is where I can put my, oh, this is where sample data exists, but I don't need that. I just want to upload my file here. So if you do this more sophisticated, yeah, usually this file will get deleted after the session. So usually if you want to have it more sustainable, you would be connecting to your Google Drive, but we will spare this. I don't think we will lose the runtime for now. Okay, did it upload our file? Yes. So this is our file. Now let's rename it because this is a weird name. We need a more interesting name. And we call it input.csv. Oh, what I'm not having in Google Collaboratory is actually GitHub Copilot, which I usually rely on to get things done. So maybe we should set up a new project, because I basically cannot think anymore without Google, with GitHub Copilot. So let's set up a real Python project here. It's funny how quickly you get used to using AI. Dun, dun, dun. And we call this Netflows, and we will put it in the Google Collaboratory in a Python notebook a little bit later. Okay, so I have a project here now, and I need to keep my window open. I'm going to put the file here. So this is our input file from which we can extract the data now. So this is in.csv, and then we need to have a main.python file that we want to use, and we want a virtual environment. So this is Python -m venv.venv. Yeah, we're creating a virtual environment for Python and activating it. So I guess if we now, how do you code? Scripts activate. Yep, okay. So now we have a Python program, a fresh Python program, and what we want is we want to install pandas, because we're very likely going to use pandas. And okay, GitHub Copilot is connected, and now we're asking it to read the in.csv into a data frame. Okay, now we have a data frame. Oh, and we need to import pandas as so just to show you what kind of data we're getting now is I'm going to do a breakpoint here, and I'm going to run this program. Okay, so this program stops, and what it does is it goes, reads this file, in.csv, and now we get the data exposed as a data frame. So if I'm looking at the debug console, this is the data frame of my data. Okay, now we have a bunch of data, and now the question is, how do we make sense of it? Because basically now we have a table in Python. Okay, so time is the foremost question here. What we have here actually, and we might need to adapt our query, is we only have the block number. We don't yet have the timing associated with the block number. That might actually be interesting for us. So getting the actual time is crucial at some point, but maybe not initially. Now initially in the first phase, we will just accept the block number as the denominator of time, and we just want to structure the data together based on the block numbers. So for example, if you would sort the whole table by the block number, now you get a sequential list of ARPs. Maybe we don't even need to sort it. Maybe I'm thinking too complex, and we can just throw it against a graph. So now the question is, which graph library do we pick? And usually the most popular graph library in Python is Plotly. So what we can say is draw a Plotly graph. The address, okay, bis dann. So the address column is, okay, what kind of graph do we want? We want to have this basically, is it called a line graph? Line graph, no. Yeah, it's a line graph. Okay, so we draw a Plotly line graph, and the address column is, no. Yeah, let's do the x-axis first. So the block number column is the x-axis, and the balance column is the y-axis. The address column is used to, no, not to color the lines, to describe the line. Yeah, let's try it like this. Okay, so is it as simple as that? I don't know, let's find out. This is the beauty of Python. You sometimes get surprised how easy some stuff is. But it's not as easy today. So let's see what we have here. Okay, matplotlib. Okay, we need an import, of course. So if it is that easy, pip install. But what is the true library? Is it matplotlib? Matplotlib. Yes. It's the beauty of coding. But maybe we don't even need an import. Let's see. Invalid caller address. Oh yeah, because it's not the caller. It's, yeah, we don't need. Okay, so this is not caller. Label. It's the label, of course. Okay, did we get a graph? Did we get a graph? Let's find again. No. Okay, so let's quickly research. How we do this best, and the way we do this is by asking ChatGPT. So let's take ChatGPT here. Okay, if you have any thoughts to share, please let me know. So we're picking GPT-4 for this one, and we're going to say, how do I draw a graph in Plotly in Python give me a short sample that will render the graph in a new browser tab. Okay, I'm using GPT-4. GPT-4 is a little bit, it's quite a bit slower than GPT 3.5, but in this case, we just want certainty that it is really rendering properly. So let's go with this. Okay, yeah, pip, I mean, we installed matplotlib, but let's install plotly too. Pip install plotly. Let's see if this is a true statement. Woo. Okay. Okay, now it's rendering out a short sample. So what ChatGPT is doing is giving me some imports that we're going to need to render it actually, creating some sample data, creating a sample graph. This one is more sophisticated than ours, but we're going to combine it. Maybe I should have told it to do it from a data frame, but that's good. So Pio, what is Pio? Plotly offline, okay. Okay, read, show me the same script, but read the data from in.csv into a data frame. Okay, this is more close to what we are trying to achieve. Okay, the installation for Plotly is done. But I guess we're likely going to see similar imports. So let's look at the code. This creates a part of the graph. This is the layout. Yeah, graph objects. I think these are sort of helper libraries that make rendering stuff easier. Okay. Yeah, so let's try it. What does it say? Simple line graph defines the layout and then plots the figure in a new browser tab using the file name line.plot. But are you storing this? I'm not sure. I'm not sure if this is correct. Well, let's try it and let's see. Okay, so we're copying the imports. Oops. And we're actually going down here to this one. So we're copying the imports, we're reading the file. I think we can just copy paste this almost in its entirety. Just need to change the property names. So lines.markers. Okay, so the x-axis is called block number. The y-axis is called balance. Lines and markers, line plot. So, okay, we're missing the labels. There is a column called, what is it? Address that determines the labels. Okay. So it's going to rewrite the script, but in the meantime we can already try this out and see if it works. Yep. Does it work? Yes, it works. It's just very crazy, but it's a first success. So we're showing a graph here. Okay, now it's basically a job of properly sorting the data and basically feeding the right data. So the first thing we will need to do is actually apply the labels. Yeah, text. Okay, so okay, so this one goes out, and we're creating now this new trace, and we're basically cutting it off here. Mode. line plot, and so it's not a line plot, it's actually balances over time. And we're adding a text property and call it the address. Okay, let's see what this does. It's not better. Okay. So, okay. Oh, okay. So, so this just defines the. Okay. So let's be a little bit more explicit. Let me specify in.csv. So we need to be a bit more specific. In.csv has 4 columns: address, block number, balance. Okay, we don't need balance change. 3 columns: address, block number, balance. I want 1 line per address. Block numbers might be a huge set of different numbers. We do this later. Let's go this is the next step. So it will now tell us how we can put every address into a different line. Maybe I should have used ChatGPT 3.5, it might have been faster, but again, in this case, we want good quality. So next job for us is to get every address into a different line. And what we can also do is we can sort the data frame by the block number, because I think this will be our next issue. Okay, 4. Oh, okay, so it's creating a scatter. No, it's creating a new trace and putting them all. I see. Okay, this makes sense. I'm not super familiar with Plotly, but this really helps. Okay. So first of all is we're getting a list of unique addresses after we read in the data frame. And then we have a list of traces, and we generate 1 trace for each address. For address in unique addresses, okay, yeah, what does it do? First of all, it reads that data frame, then it gets a list of all the unique addresses in that data frame, and then it iterates through each individual address, and it filters out the data frame just for that address. And then it puts all the data into a trace, and a trace is basically like 1 line on the thing. Okay, and then we're creating the layout. And the data here is the traces. Okay, this sounds better, and curious to see what we're getting. Yes, this looks a lot better. Now we have different addresses. Now it's still chaotic, and I think this is where we have to sort through the addresses now. So we're going to do this here, because this will be, so sort by block number. Yep. Okay. Good. Yes, this looks like data we can actually use. It's a little bit ugly still, but this is something we can already work with. Okay, so it draws a dot every time there is actually something happening, and it renders out fairly nice. So this was far easier than I anticipated. We got this done in 30 minutes. This was with a lot of talking. Okay, now we have an obvious problem, and the obvious problem is, what do these addresses mean. Okay, so what can we do here? We can take an additional file to from our addresses here and use that and cross the data. We cross the data, we basically determine the name here, and this should be good to provide some information here. So I'm pasting this here, and I'm downloading this as a comma separated file, and we're going to drop this here, and this is now the labels. So this is the labels. Okay, so this is called the data. No, this is the data frame. This is the values data frame, and then we have a labels data frame. Okay, and so we need, where do we need the label? We need the label here. So the label is checking the labels data frame for the address and is looking for label, but in this case it's not label, so it's checking for big address and big chain. So this is basically checking for capitalized address and capitalized chain, maybe, and then we would apply the label here. Yeah, I think this should work, but let me check. Okay, yes, this works, so we can let this run. Yes, and here we have the name of the chain. So blue line is, okay, this is making sense now. Okay, we were actually pretty far with the basic proof of concept today. So what do we have here? We have a blue line that is moonbeam. So the thing we're still missing here is time, but let me give you a rough approximation. Block 14 million on Polkadot was the beginning of this year, was it? Polkadot.subscan.io. Oh, yeah, I think it was. Yeah, it was. Oh, okay. It was the end. It was the end of January. So this, we can improve this graph by actually merging in, basically crossing block number and the actual dates. This would help give us an indication of time. But let's get a rough indication of what this time means. So what is 1 million blocks here? Okay, so we have 10 blocks per minute. We have 60 minutes per hour, and we have 24 hours in a day. So this is 69 days. 1 million block is 69 days, so 2 months, a little bit over 2 months. And 3 million blocks is 7 months. So a million block is 2 months. So this is 1. So this is 7 months. So this is a year, roughly a year of activity, of course, because you can see here is likely when the first parachains went live on Polkadot. They already had the experience from the Kusama network on how to transact value, so they could start into XCM roughly at the same point in time, right? So you can see those chains here, and then you can see. So first one was statement starting out here. I'm missing some data here, so something is off here. Maybe the scan here ended prematurely. So let me quickly reinitiate that one so that we can correct this. So this is a statement, and we have There's still Kusama here. Yep. So we're going to rescan this address. Maybe I missed it because, you know, sometimes the scan fails and then I have to restart it manually. But this looks interesting to me. It thinks it is done. Okay, I will find out what's wrong here later. But let's look at the data a little bit and appreciate what we have. So we have Moonbeam. Moonbeam, biggest player that we can see here. Where do we have Akala? Should be orange, but no, this is Akala. Oh, I confused statement and Akala. Oh, it's possible that they stopped XCM transfers in August. Not sure. I have to take a look. Okay, we have the Vinia. Interesting. The Vinia is having some good value locked here. What do we have? Oh, 10 to the power of 16. So 10 to the power of 12 is 1 KSM. So 10 to the power of 16 is 10,000 KSM. Dot. We're talking dot. Dot is 10 to the power of 10. So this is 10 to the power of 6. So this is like a million dot. I think there should be more than a million dot, or is it a million? 10 to the power of 16. We have to take a look. You know, let's look it up. So how can we look up how much value is actually in a Parachain? This is something that you might be interested in. We're going to look at the Parachain dashboard here. And we're going to look up Moonbeam, and we compare the data that we see in our graph and compare it with the actual live information that we see on Subscan. So we have Moonbeam here, and we can learn everything about Moonbeam. And if we go into the Polkadot sovereign account, we can learn how much dot there is in Moonbeam. And it is 1 million dot. Interesting. So I think in all of Polkadot we have 120 million, if I'm not mistaken. No, 1 billion. Is it 1 billion dot? I think it's 1 billion dot. Let's look at polkadot.js.org/apps. Let's look into Polkadot and see how many dot there are. Explorer. Yeah, it's 1.3 billion dot. And 1 million dot is a Moonbeam. That means there's actually a lot of potential for XCM still. This means there isn't. I would have expected there to be much more dot. I would say 10 times the amount of dot actually in Parachains. Because this means, would it mean there were 3 million dot? Would it mean there were 3 million dot in Moonbeam before? But here it shows 1 million. Curious. Yeah, okay. So this stopped a few weeks ago. So we would have to compare it a little bit. But maybe this is let's start taking notes because there are so many ideas on how to improve this. So improvements. Number 1 is date instead of block number. Then Moonbeam has 3 million dot in the graph in the end of January, but 1 million on Subscan on today. So we can compare this data a little bit. Then we could make the graph nicer. So that could be remove the dots. remove the dots, and yeah, maybe this is enough for the beginning, and improve the description for the y-axis is something that I would also like to do. Okay, but so this is some things that we can do now. Okay, this actually looks fairly nice. Another thing we can do is look at the data of Kusama and compare this a little bit. What type of history can we see on Kusama? Before we look into Kusama, let's have a final look and compare the chains. Okay, so we're seeing Moonbeam here. We are seeing Parallel here. What did I say before? I said Darwinia. Okay, I've been looking at the legend again. So if I cover this here, so this is Parallel. Interesting. Okay, then we have Interlay. Yeah. So Interlay is holding collateral to mint KBTC, IBTC. Okay, this is A star. Okay, you see there was a quick rise here. Then there was some capital dropping out. Okay, and these are now, the other chains are now having the Bifrost that the scale is a little bit different for them. So there are two things we could do. We could filter out, we could basically have two segments, the segments for the chains with more capital and the chains with less capital. Or we could apply a logarithmic scale. So maybe to start out, it would likely be simpler to apply a logarithmic scale. Can we do this here? Apply a logarithmic scale. So okay, let's see if that works. Yeah, okay. Logarithmic scale, of course, looks different. It might not tell us as much, but at least we can get a quick look here. So we have 1 billion, no, 10 billion, 100 billion, 1 trillion. Oh, and we have to divide everything by 10 to the power of 10, maybe, to make it more readable, because we don't, my brain can't process the numbers. So how can we do this? We can do it here. Divide, so decimals equals 10. And now we say divide balances by 10 to the power of decimals. Yep. And then take another look. So yeah, it's so it's 10 to the power of decimals. Okay, so this should become more readable now. Okay, I'm getting too much stuff going on here. So, and I would prefer to have it rendered in this browser. Okay, yeah, so this is Polkadot, and it's much more reasonable. This is now in dots, so you can see, for example, this is 1 million dot, 3 million dot, okay, 100,000 dot for A star, 10,000 dot for Bifrost. Also, okay, Hydra DX is coming in here strong, and then we have a few smaller ones. So Fala is having a few transfers here in the range of 100 dot. So maybe these are trace amounts or test amounts. So they've been testing affinity also, Clover network, unique network. Okay, so you see they have been all testing here. Okay, but besides that, the logarithmic scale doesn't speak too much to us, so I'm going to remove this one again. And now that we have the rough framework here, we can look at Kusama data and also get a feel for that data. Okay, where is it? So this is where we do the logging. I will put it in an extra line, comment it out. Okay, yeah, so let's do this as the final part of today. Look at the Kusama Netflows. And I think that's a nice piece to conclude the session then for today. So, I would say I'm going to save the script. I'm going to save this query, Netflows data. Good. Okay, so I'm going to write another query, and maybe while we have the opportunity, we can also merge it with the date information. So at which time, at which block. And how we can do this is by joining the data with, I think I have this in blocks, alpha chain, Polkadot. So let's look at the blocks data. Yes, and it has a timestamp. So join balance changes. Oh, let's call this table changes. Changes dot address. Changes dot block number. Changes dot balance. And that's actually enough. We don't need the balance sheet. Okay. And then we join it with a table that is called blocks. Blocks, and we change it on changes dot block number equals blocks dot number, and then what we can then select is blocks dot timestamp. So let's see if that works. Query executes. Okay, and we have a timestamp here. Excellent. Yeah, let's use the data. So download the file. Yeah, and then maybe we will have, I have to do a little bit of casting when we use the Python data to prepare it for the rendering. But this is also a nice side quest. So let's open this here. We're going to delete the original file, use the new file, name in.csv. So this means instead of the block number, we're now going to look at the timestamp. And so I think just using the timestamp won't be enough. I think we have to cast it, but let's try it out first. I think it will be interpreted as a string, but maybe we can rewrite it already when we load it. Convert the timestamp to, it's predicting my faults. You know, let's see if GitHub Copilot just predicted my fault. This is interesting. Okay, so we have values df, and this is the timestamp how it looks like now. And then if we go, yeah. Okay, so what I'm going to do is again go the lazy route. and ask ChatGPT. Because asking ChatGPT is the laziest thing I can come up with. So give me ChatGPT 4. Okay. So I am adding a column called timestamp to in.csv. The timestamp has a format like in this sample. Please provide a code sample that properly casts this string when it appears as a column in the data frame. Okay, so it suggests the PD date time thing, which we already see here. Now the question is if it comes up with different parameters. Parse dates. Not sure, but let me try. Maybe everything is always simple in Python. It's possible. Parse dates. Timestamp. Interesting. Okay, so let's look at the values data frame. Was it properly parsed? This looks like it was properly parsed. I'm impressed. Okay, so I think then we can use this. We don't need that anymore. Oh, is it having a harder time now with the date time? Ah, yeah, okay, much better. So we can see now the month. Yes, so it's giving us the date now. Very well. I'm very happy with this result. So on the y-axis you can see the proper amount of tokens, and on the x-axis you can see the date. So let's change those descriptions, and then we are approaching a truly nice graph. So this is date, and this is dot. Yeah, dot balance. Everything else is gone now. Isn't this weird? Oh. Yeah, but still everything else is gone now. This doesn't look like what we saw before. Does it? Did we change anything? Was the scale different? The scale was different, was it? We should define the scale that we want to see. No, the scale wasn't different, was it? Oh yes, the scale didn't start at 0. That's the difference. So we should define where the scale should... No, that cannot be the problem. Huh? Okay, maybe... So this is 5,000 dot 11,000. It's actually small values when you compare it. I mean, the only thing that is different here is this one, but then I think we got it Didn't look any different than this. Okay, we will find out later. Maybe we should start to take a look at Kusama now and compare those values. And maybe I'm going to look one more time into this mode to check the logarithmic data again and take another look, because I think we saw more lines previously. Do we still have one of the other graphs intact? Not here. I have a line from previously. Oh, okay, so this was 500,000. Look, it showed more data. Something's off. Yeah, the scale changed. Okay, I think I know what happens. I think maybe I made a mistake in the recalculation. So So this time everything should be exactly as intended. No. Okay, then let's comment it out completely and see if that works. So the other possibility is when we change the query, the data also changed. But that would be odd, wouldn't it? Okay, so the curves look the same, it's just that they have different values. So here it has 3.5 million, and what do we have here? 4 million. This is very different. Maybe it is compressing the data and only showing some data. No, but that doesn't make sense, because, for example, parallel should also be happening here. Maybe no, but these values match. It's only the extreme values that are different. Akala 4. Seriously confused. And there is some data missing. There's, for example, parallel is missing here. This list is shorter also. Okay, so my next assumption is something about the join was wrong. On change this block number as blocks number. Okay. This is not an on-chain mystery. This is just a mystery of what am I missing here. Oh, we don't yeah, we don't actually need that. We have it downloaded, so I can just pick it from the download folder and change it. So okay, I'm going to give this 5 more minutes, and if we can fix it, I'm going to solve this on my own. So this is version 2, and this one was the original version in 1. So we're going to take a look at in 1, and this wasn't timestamped, this was block number. Block number. Oh yeah, and good. Okay, is this the thing we just generated? Yes, so the original data is different from the data we have here. Okay, so now we can generate the new one on the server and see if we're getting a different result, or what happens if I comment this out and so on. So, but this should be identical to what we just saw. Looker Studio, Collab Notebook. This would also be interesting. Let's just click on this button and see what happens if we open it up in Looker Studio and what Looker Studio actually is. Maybe this is like an onboard visualization tool that we can use. That looks interesting. That looks interesting. Okay. So what can we do? We can say add a chart, and we want a line chart time series. Okay, so the dimension, I guess, is it breakdown dimension? Starting to guess it's the address. So no, the metric we're looking at is the balance. And maybe dimension is time. I guess time is the dimension they're looking for. Invalid missing dimension metrics or filters. Okay. This is a result. Breakdown dimension. Okay. Can we get some help somewhere? Okay, let's look at how this is done here. So this names the address as the dimension. So in our case, it would be the block number, yes. And then it doesn't have anything, and the metric is the block number, so this is the y-axis. So in our case, the y-axis is the balance. So block number and balance should be right. And maybe breakdown dimension is the address in this case. No, the address. Can you see some errors here? Time series filter. I don't know the time series filter. Matrix, record count, dimension. I see. But this is actually, can I pull this down? Balance? It's not a dimension, it's a metric. Maybe this is the error. Okay. Create a line chart in Looker Studio. So dimensions. Dimensions of data. I will research this on my own. And we're just going to download the data now, compare it one more time, then decide on which data set to use. Then we're going to use that data set, and I'm going to make some additional checks a little bit later. And then we can already prepare the query for Kusama. Okay, so we got this now, and let's call this inversion free. Okay, and we're going to check this one and see if it looks the same as in version 1, and if so, then the problem is just in our applying the dates, and then we can fix the dates later. Okay, so then there is a problem in the join, and we will not think about that now too much. Instead, generate some more data. Oops, it's not right. This is not right. This is not right. Huh. I think I lost the right browser window. Okay. Netflows data. Good. Yeah, so in this case, we're not going to fix it right away. We're going to look at Kusama data and don't care about the time dimension. So then we have one last nice thing to show for today, and everyone should be happy. Okay, so let's look at the Kusama chains here, and we're going to put all of those in a new list that we're checking against in Google BigQuery. So this is a list of all the Kusama parachains, and we're going to give this list of all the Kusama parachains here. So okay, there's a query for all the Kusama parachains, but we have a few more blocks. We have actually, I think, 15 or 16 million blocks. Let's create like this. Unexpected bracket, still line 33. Unexpected closing bracket. Oh, yeah, okay, of course. So, okay. Good. So we're getting Kusama data now, and can have a look here on the Kusama data. No results. We want to query Kusama. Yes. Okay, so this is our Kusama result. We're storing it as a file. It's going to download in a second. And what I'm going to do is delete this here, and this is called Polkadot CSV, and these are the Polkadot labels. And so we can have, this is Polkadot. Okay, let's say values, the values file name is Polkadot CSV and labels file name. Okay. So, okay, this is a little bit generalized now. This is Polkadot labels, and for our next attempt we're doing the same thing for Kusama. So we're going to show Kusama data. Okay, and first part of that journey is by taking that file that we just downloaded, which is our Kusama data, and we're going to name it Kusama CSV. And now we need the Kusama labels, and we get them by applying some magic here. New sheet, this, download as CSV file. There is a download. We add the download here. This is Kusama labels, and I think we can hit F5 and see our data for Kusama. Good. Huh. Good. Interesting. Okay, let's see what we have. So, Heiko? No. This is Karura. Yeah, also recently stopped. Okay. Then we have Bifrost. Yeah, it seems like I'm missing some data here. I'm pretty certain that Bifrost did not stop having XCM transfers. So I have to look into that issue. Okay, what else do we see? We see Moon River here. I'm not sure that those had such a distance here. So I think something about the data isn't right. Something about the data isn't right here. Okay, I need to apply some different decimals here. So, where's the decimals? Okay, we know that this calculation wasn't the issue. So, we know that in the case of Kusama, the decimals are 12. Okay, so there's a 160,000 KSM. I would believe that Moon River had much more KSM than is shown here. So there's something off with the source data that I have to check out, and I will compare this later. So we have to see all of those data with a little bit careful. I know that the number of tokens from Mangata looks right here. So there's an indication that the data is right, and I'm not so experienced in other chains. But it's sort of, the sizes roughly match. You have Kintsugi here, you have Heiko here. This is Mangata with the similar coloring. This is Basilisk, and then we have a few other chains. Okay, so this is roughly the correct data, but there are some questions here around why is Bifrost data cutting off? Was this due to the cutoff here? And then, do we have state mine? We have state mine here, but I can't believe that state mine only has 44 KSM. I mean, it doesn't need too much KSM, actually. Interesting. This is going to be interesting to see. Okay, but what we can see here today is we got two charts from the raw data. So this is both Kusama. Do we still have a chart from? Yeah. So this is a Polkadot chart. This is a Kusama chart. Let's put them side by side. Okay, so this is a Polkadot chart. This is a Kusama chart. You can see similar growth actually for them, but applying the proper time frame would be interesting. But I think we got some pretty nice results for today. I think I'm going to make them a little bit more nice, and then I'm going to share them on Twitter. And so with this, I would like to end the stream for today. I see that one concurrent viewer was here all the time. Thank you for being here. But yeah, I think it's just interesting to show how the actual journey goes and how we're exploring those kinds of data. And I'm going to do more of those streams. I think it's a very interesting way to challenge myself to show some interesting stuff and then like build in the open and share what we got. So thanks for tuning in for today. Have a good day. Good night.